All right. Hello, everybody. We are looking at the continuation of section 1.5. This is 1.5 continued, and we're talking about the average rate of change. So remember that from Algebra 1, the slope of a line can be interpreted as a rate of change, but in this section, we're going to be looking at the average rate of change. So for a nonlinear graph, the average rate of change between any 2 points on a function is going to be the slope of the line that goes through those 2 points. And the 2 points can be, written as x1 comma f of x1 and x2 comma f of x2. Those could be any 2 points on your function. And if we draw a line through those 2 points, we can talk about what's the slope of that line, and that line would be called a secant line. All right, so I think it might be best to take a look at this in terms of an actual example. So the average rate of change, and by the way, here's our formula for the average rate of change. The average rate of change of a function from x1 to x2 is given by this very important formula. So I'll put a star by that. All right, it's f of x2 minus f of x1 over x2 minus x1. So here's my example. I've got this function right here, and let's say that the function happens to go through -5, 0, and -2, 2. All right, there's my function, and I want to know what's the average rate of change from -5 on the x-axis to -2 on the x-axis. That means that I can figure out what my ordered pairs are. x1 comma f of x1 is going to be the ordered pair -5 comma 0. Everybody with me?
So is it pretty much just the same thing as saying y2 minus y1?
It is very similar to that. Very similar to the slope formula of y2 minus y1 over x2 minus x1. The only difference is we're talking about our y's in terms of what's the function value at that x.
Okay.
So, but very similar idea. And so then this is, the other order pair would be x2 comma f of x2. And so for my example, that would be the order pair -2 comma 2. Are we okay with this? So we're really trying to find the slope of this tangent line that goes through -5, 0 and -2, 2. That's the, I'm sorry, did I say tangent line? My bad. Secant line, right, that goes through those 2 points. So to find the slope, we're going to use this formula, all right, but that is the same as y2 minus y1. So I'm going to write my formula again. That's f of x2 minus f of x1 over x2 minus x1. And so in this case, I could really write this as f of -2 minus f of -5 over -2 minus a -5. Slide this down a little bit. Does that make sense? Because my x2 is -2, so I want f of -2. My x1 is -5, so I want f of -5 in my numerator. And so what values am I going to be plugging in here? Some help, Chris.
You're going to be plugging in. So when you start out the fraction, it'll be 2 minus 0 over -2 minus -5.
Do people agree with that? Okay, and so I get, what, 2 over, this is -2 plus a positive, is that 2/3?
Mm-hmm. Yeah.
All right, so the slope of this line is 2/3, the slope of the secant line. And I think we could see that because if I want to go from this point to this point, I'd have to go up 2 and to the right 3. So the slope is 2/3. Gabby.
That's right. So how did you get the 0?
Chris, where did the 0 come from?
It came from in the the ordered pair of x1 f of x1, it's the 0.
So what formula?
So this is our formula, right? But we're trying to specifically find the average rate of change from -5 to -2. So I just filled in -2 for my x2, -5 for my x1. Now what is f of -2? I could either look at my graph and see, hey, it goes up a height of 2. So f of -2 is 2. And what's the height of f of -5? I can look at my graph. At -5 over, it's at a height of 0.
Okay.
Is this okay? All right. And we could graph this, and I would love to, but I think we should move on. So let's take a look at this example. This is now doing the same thing, except I'm not showing you a graph for this one. So let's just follow the formula. We want to find the average rate of change for f of x equaling x squared minus 2x. And we're going to go for x1 is 1 to x2 is 4. So in this case, again, our formula is f of x2 minus f of x1 over x2 minus x1. And so we are plugging in f of what minus f of what over what minus what. Can you fill in those blanks for us, Patrick?
F is 4.
F of 4 minus f of 1 over 4 minus 1. So I guess we're going to have to figure out what is f of 4. So maybe off to the side here, work out what is f of 4. And we need to know what's f of 1. So you want to do that off to the side. Can you help me out with those, Lexi? What's f of 4 equal to? Here's our function. How'd you get 8?
So I put 4 in, but f of 4 equals 4 squared minus 2 and 4.
Okay, so 16 minus 8 gives you 8. All right, how about f of 1? What's that going to be, Veronica?
You do 1 squared minus 2 times 1 is negative 1.
-1. Are we okay with this? So filling these values into our formula down here, Kelly, can you help me out with that?
You would have, you put 8
8,
plus 4.
because it's minus a -1,
Yes.
over.
4 minus 1.
All right, so you got 8 plus 1, that's 9 over 3.
Yeah.
And we're getting the slope of our secant line is going to be 3, and that's the average rate of change for this function. That's kind of a measure of how fast this function is changing between 1 and 4. Are we okay with this? All right, and let's see. Let's take a look at this in the context of a real-life problem. The distance s in feet of a moving car from a stoplight is given by s of t equaling 30 times t to the 3/4 power. Find the average speed of the car from its stopped position at the stoplight, right? That would be t sub 1 equaling 0 to t sub 2 equaling 5. So we want the average rate of change. All right, so we want to know what's the average rate of change in the first 5 seconds after the light changes to green. All right, so again, we're going to be using our formula. In this case, I would say we want s of t sub 2 minus s of t sub 1 over t sub 2 minus t sub 1, right? Instead of f and x, I'm using s and t. So can you help me fill in some of those values here, Megan? So what am I filling in for T1?
For T1, you're going to have 0.
And what am I filling in for T2? So I'm going to rewrite this as S of 5 minus S of over
5.
Everybody okay with this? Nora?
How did you know whether to use S of T or T sub 2 as the X value? So like X2 minus X1. Oh.
because I just used S and T instead of F and X, right? It's the same formula, I just used I used T's instead of X's, and I used S instead of F. Is this okay?
Yeah.
All right, and so at this point, you are getting some values for this. You reach for your calculator. What's S of 5 equal to on your calculator, Dan?
It's going to equal 3 times 5 to the 3 over 4 power, or 30 rather, times 5.
Okay, wait, so we're trying to find S of 5, so isn't that 30
30
times 5 to the 3/4 power? Okay, and what, did you get a decimal for that, or what'd you get?
Yeah, it's a decimal. Let me go, sorry. It's about 100 points. Well, how many decimal?
Just like 3 decimal places sounds good.
All right, so 100.311.
100.311.
311.
Are we okay with this?
Yes.
And S of 0 is equal to what?
0.
0. So it looks to me like we're going to get our answer by taking 100.311, that's supposed to be a decimal point, minus 0 over 5. So that means that's about what? 20 something? Yes? 20.06? 062. Are we okay with this? So the average rate of change would be 20.06 what?
Feet on feet.
Seconds?
FPS.
Feet per second, right? All right, so 20.062 feet per second. Okay. That was the first part of what we need to talk about today. And the second and last part is talking about the fact that functions can be considered even or odd or neither. All right, so functions are either even or they're odd or they're neither. And we have 2 ways for telling whether a function is even or odd. All right. First is a graphical test. And so a function is going to be considered even if its graph is symmetric with respect to the y-axis. So, for example, if I have a graph that looks like this, what kind of shape is that? Parabola. And we get those from looking at f of x equaling x squared, right? F of x equaling x squared would be an even function, right? Because we have mirror images of this graph over the y-axis, right? Mirror images. So it's symmetric with respect to the y-axis. So f of x equaling x squared is even. All right, if we have a function that is odd, then its graph is going to be symmetric with respect to the origin. All right, and so one of my favorite odd functions would be f of x equaling x cubed. And we didn't look at these graphs yet. Do you know what x cubed looks like? It is kind of a squiggly shape, right? And we're going to be studying these parent functions, x squared, x cubed, square root of x, absolute value of x, all in the next section, 1.6. All right, which, by the way, is going to be homework after your quest, is to watch a video on 1.6. I think it should be a little bit more lively video because it was recorded in front of my Block 2 last year. So you'll get to hear some names that you know and so forth.
Thank you.
What's that?
Thank you. Us right now.
You sound kind of faint if you watch the video, but yes, you can. If somebody has a strong voice, it's probably carrying over right now onto a video. Until you said that, I totally forgot we were recording. Hello, everyone. All right, so x cubed graph. I hope I didn't say anything bad. All right, x cubed graph looks something like this. What was the way that we could tell? We talked about this back in the appendix, back in August. How could we tell by looking at a graph if it was symmetric with respect to the origin. We had a way that we could tell. Megan?
It was x, or the like original form would be x, y, and then the other two would be negative x, negative y.
All right, so xy on the graph would always match up with a negative x, negative y on the graph. And then what was the other way that we could tell, just by looking at a graph?
Within 180 degrees.
All right, so if we do a 180-degree spin test on this, and we should get right back to the original. Okay, obviously, all right, that's bad. But you get the idea, right? Okay, so 180-degree spin test, if that works, then you have a function that is odd. All right, so this is an example of an odd function, and the graph is, oh my goodness, is supposed to be symmetric with respect to the origin. Okay, so those are the graphical ways to tell, but we also have algebraic ways to tell whether functions are even or odd. Yeah.
What would it be if it was like this way?
If a function, you mean look something like this?
Yeah.
Yeah, that would be an example of a graph that is symmetric with respect to the x-axis, but first of all, it's not even a function, is it? No, because if I try and do a vertical line test, it's going to fail. So graphs that are symmetric with respect to the x-axis probably are not functions.
And then what about the ones where they look like two boomerangs on each side?
Two what?
Boomerangs on each side. I don't know what they're actually called.
Boomerangs.
They were in the
Did you see some of those on the homework?
Yeah.
Yeah, something that looks like this maybe,
Yeah.
with something that looks like this.
Yeah.
Yeah, nice looking graphs. We're going to study these some more in chapter 2. I think this is 2.7, but we won't get there until, late third quarter, early fourth quarter, because we are going from chapter 1 to chapter 4. We start our trig unit. We're going to be in trig for like 3 months. And then we'll come back and do, well, we do 4, 5, and 6, that's trig, and then we come back and do 2 and 3. So this is near the end of the year, we'll talk about these. So can you hold on until then, Gabby?
Yeah.
All right, so let's take a look at our algebraic ways of telling whether we have an even function or an odd function or neither. So if you plug in negative x wherever you have an x, and you end up getting right back to the original equation, the original function, then the function is even. So here's an example. Let's say I have this function. F of x is equal to the absolute value of x. If I want to test whether this is an even function or an odd function, I would start off by plugging in negative x wherever I see an x. So I would want absolute value of the opposite of x. Is the absolute value of opposite of x the same as the absolute value of x? Yeah, no matter what number I put in here, whether it's positive or negative, it's going to be the same as if I had put the opposite one in. Correct? So since that is equal, that means that in this case, f of negative x really does get me back to the original function, f of x, and so that means that this function is an even function. And I know we didn't study this yet because it's our next section, 1.6, but when you look at the graph of an absolute value function, f of x equaling absolute value of x, the graph looks like the letter V with its vertex right at 0, 0. Does this have symmetry with respect to the y-axis?
Yes.
Sure does. Mirror image over the y-axis. So that is an example of an even function. All right, and for f of x, no, let me try another example. This is our test to see if we have an odd function. If you plug in negative x wherever you see an x, and you don't get the original back, but you get the exact opposite of the original back, that's your recipe for an odd function. So let's try a sample. Let's say I have f of x equaling 4x cubed minus 7x. I'll leave it like that. 4x cubed minus 7x. And I want to tell whether this function is even or odd or neither. Well, I would plug in negative x wherever I see an x. So I would have 4 times negative x quantity cubed minus 7 times negative x. if I have negative x times negative x times negative x, is that going to be equal to x cubed or the opposite of x cubed? Opposite. So I really have 4 times opposite of x cubed, which is the same as negative 4x cubed. And then I've got a negative 7 times a negative x, so wouldn't that be a plus 7x? So I get negative 4x cubed plus 7x. Is that the same as my original? No. But if I factored out a negative 1, would I have negative 1 times my original? Yep. Yeah, so I really get the fact that f of negative x is equal to the opposite of my original function f of x. So I just concluded that f of negative x is equal to the opposite of f of x, and that's my recipe for an odd function. Let's graph this one just to see if it would pass the 180-degree spin test for an odd function. That's 4x cubed minus 7x. Graphs. I want 4x raised to the third minus 7x. Does that look like it would pass the 180-degree spin test?
Yes.
I think it would. Yeah, if I could rotate this 180 degrees. Are we okay with this? All right, so we've talked about average rate of change, and we've talked about even functions, odd functions, and obviously there's a whole ton of functions that are neither, right, even nor odd. Okay, so that finishes our notes for this. Thanks for watching.